Everybody, this is John Mankowski, coordinator for North Pacific LCC. Welcome to our science management webinar on the Washington Connected Landscapes project. There are a few more people dialing in and logging in, so we will talk about just some of the logistics for this as people join the group. With me here is Megan Carney, our outreach specialist, and we have two guest presenters whom I'll introduce in a minute. By way of introduction, the NPLCC spans the region from south central Alaska, the entire coastal temperate rainforest down to northern California, and we work primarily in providing information, science tools, and capacity to help natural resource managers incorporate climate change into natural and cultural resource conservation efforts. This project was funded in part by us and in part by other conservation groups and the Great Northern LCC in 2011, and it's really designed to do two things: provide some tools and techniques to promote landscape conservation, particularly from the perspective of corridors and migration corridors for wildlife, and also to add to that climate change overlay. So NPLCC's interest in funding this project, or partially funding this project, was to ask that this tool be created, that this information includes climate change assessment, and that it be made widely available through a website so managers can use this information when they're contemplating landscape scale conservation planning or design and are interested and concerned in maintaining and protecting future migration corridors and how climate change may affect that in the future. With us this morning are two of the principal investigators. First up is Dr. Brad McCrae. He's going to give a presentation on the tool and how it works and what goes into this planning tool. Brad works for the Nature Conservancy. He has specialties in conservation planning, climate change, connectivity, and ecosystem services. And then he will be followed by Dr. Mead Crosby, and Mead is with the Climate Impacts Group up at University of Washington, who spends a fair amount of time working on climate change impacts and adaptation, conservation biology, species boundaries, hybrid zones, and species range limits. The two of them collaborated on this project. Again, this was funded in part by the NPLCC, but also the Great Northern, and I believe the Wilberforce Foundation.
I'm Brad McCrae, and as John said, I'll be talking about tools that we developed with NPLCC funding. I will be describing the tools in some detail, and then Mead will be presenting a worked example in Washington State. As John said, we developed these tools, and it's really a family of tools with NPLCC funding. But this was really, when we proposed this work, it was really a cross-NPLC or cross-LCC proposal. We were proposing to develop the tools with NPLCC funding, but test them with GNLCC funding in eastern Washington. At the time, we had mapped corridors for 16 focal species across Washington State and neighboring landscapes, and we had also developed a method and prototyped it in Washington, mapping corridors for climate change, corridors for species range shifts under climate change. But we had a lot of work to do at that point. The corridors we had mapped for the 16 focal species showed where the best movement routes were between different core habitat areas, areas that have high amounts of high-quality habitat for each species. And you can see those routes in yellow here connecting each pair of patches. But there were a lot of questions left unanswered even when we looked across all of our focal species. The first was the need to be able to replicate these methods in new geographies and at different scales. The climate corridor tool approach that we had developed was extremely cumbersome, took probably weeks of GIS analyst time to implement. And the corridors we had identified, again shown here with the best movement routes in yellow, didn't really give managers enough information to implement connectivity conservation action. it didn't tell them which corridors were most important to keeping the entire network connected, in this case for ELK. It didn't show where corridors were most vulnerable. For example, these bottlenecks down here in southern Washington, where the loss of a small amount of movement habitat could disconnect two core areas completely. And it didn't show where you would put your investment into connectivity conservation versus restoration. So to give a little bit more detailed example of what I'm talking about with those latter points, I'll use our favorite focal species, the 17th out of 16 focal species, the star-bellied sneetch. And any resemblance in habitat or resistance maps to the sharp-tailed grouse are purely coincidental. So for our work, we first would map core habitat areas. These are areas that have concentrations of high-quality habitat. And this was done with one of the schools that was ultimately produced and made available with NPLCC and GNLCC funding, the gnarly landscape utilities. We would then map landscape resistance, and because sneetches avoid human development, urban areas here are shown in red. Those are areas of high resistance, difficult areas to move through. Natural habitat is shown in dark green. Those are areas of low resistance. And barriers that are semi-permeable, like the Columbia River here, are shown in intermediate colors, light green there. We've also created a tool within the gnarly landscape utility package to automate resistance mapping, and this is all based on satellite imagery, different maps of land use and land cover, roads, etc. So the Linkage Mapper toolkit allowed us to first automatically identify which core areas could be connected, and then automatically map least cost corridors. And I'll zoom in to one of those, talk about some of these issues that we were trying to address with this project. So as I said, we take satellite imagery and maps of roads and other features, classify that into a resistance map using gnarly landscape utilities, and map the routes of least resistance connecting the core areas. What wasn't apparent from these products were how a manager would prioritize conservation actions within these and among these corridors. For example, which corridors are most important to keeping the network connected? Which are vulnerable and where are there bottlenecks in corridors? And where are there barriers that could potentially be restored to improve connectivity? So focusing on that first question, again, this is that network of core areas produced by Linkage Mapper. And our first tool was a tool that used CircuitScape to map where we have cores and corridors that have high centrality. Essentially, core areas and corridors where the loss of a core area or a corridor could disconnect large proportions of your network. And so here, this central core area, if these are the only movement routes available, if we lose the central core area, we would disconnect most of the core areas from one another. So we would really lose a lot of connectivity across the network. The same goes for this corridor and this corridor right here, the purple ones. Those have higher centrality than the corridors that only connect single core areas. So if you lose this corridor, you would disconnect this core area from the rest, but that's really the only loss in connectivity you would have. If you lose this corridor, you disconnect two core areas from the rest of the network. The second tool in this toolkit identifies pinch points or vulnerable areas within the corridor. So if we zoom in on that corridor again, this identifies areas in yellow where connectivity is most vulnerable. So if you think of this, this is again using Circuitscape, and if you think of this again in terms of flow from one core area to another, here you have a very broad area where the loss of a small chunk of movement habitat wouldn't have a big impact on connectivity. But as you move southward, you get into areas where all of the movement is concentrated in small portions of the corridor. There are barriers, for example, the Columbia River right here, and agricultural lands that funnel the movement and create movement bottlenecks. And this tool identifies these areas. They show up in yellow here. And that's an area that you want to make sure is protected because the loss of a small amount of habitat could really adversely affect connectivity. And the last tool identifies barriers, some of which might be restoration opportunities. So why would we want to model barriers? Well, first of all, connectivity conservation focuses on protecting important movement areas like these corridors along riparian areas. But it also focuses on restoring areas that might be impeding movement, whether it's restoring agricultural areas for sage-grouse movement, putting in a culvert for, in this case, a black bear to move across a highway, or even putting in a highway overpass like the ones that are slated for Interstate 90. And we need to know where the best opportunities for that might be. And this is what the network looks like when you apply the barrier tool to it. It shows where you have the greatest, where you have areas that are impeding connectivity the most. So again, in that one corridor, it highlights areas where, if restored, the movement ease between the two core areas would be greatly improved. Here are those barriers shown on top of the resistance surface, and there's not much we could do, for example, about the Columbia River, but there's a lot we could do about this road down here, and it even identifies restoration opportunities that fall outside of the current corridor. This is a power line over here, which sneetches are want to avoid. And if we restore that area, it actually reroutes the least cost corridor. You still have all of the movement opportunities that you had before in your original corridor, but because we've removed this barrier, the best route is now down through this southeastern corridor. So you're creating a new corridor, you're reducing the overall movement difficulty, and you're adding redundancy to your network. You have multiple pathways now that connect those two core areas. So I would argue that this really opens up a lot of options for managers because they're not constrained to just working in this particular landscape or this particular corridor where you might have landowners that are not interested in efforts to promote connectivity, or you may have high land prices or development pressures that don't exist over here. And with NPLCC funding, we published this back in 2012, and this is now being taken up in different landscapes. So I want to switch now to talking a little bit about mapping corridors for climate change, and this is an effort that Mead really spearheaded from the beginning, and she will go into more detail on. But our purpose in focusing on this was to identify corridors that would be important for species range shifts. Range shifts have been the most important way for species to respond to climate change in the past. And because the rate of climate change will be so high in the future, species will need to move farther and faster than they have in the past to keep up with climate change and shifting habitat. What's different as well from the past is that we now have human-imposed barriers on the landscape. And human land uses will impede movement for a lot of species and really throw a wrench into the works for range shifts in response to climate change. So Tristan Nunez, Mead, Josh Lawler, Josh Tewksbury, myself, and others developed an approach to map what we're calling climate gradient corridors. This approach simply assumes that species will need to cross climate gradients, for example, moving from warmer areas to cooler areas. And while doing so, they will need to avoid human land use in developed areas. Our approach identifies large patches of natural land that differ in temperature. So these are temperatures today. And we assume that those temperatures will change, but the relative differences will stay roughly the same, that this patch will always be cooler than this patch. So we're assuming that these climate gradients are more or less conserved. So we're not predicting how the climate change, we are simply assuming that it will change. And we are identifying networks of core areas that differ in temperature so that as the climate changes, at whatever rate it changes, species will be able to move, say, from this yellow temperature band to new habitat areas that are amenable to them. We also assume the methods then map corridors that avoid areas of heavy land use, and it takes into account the climate gradients between those core areas. So, for example, if you are a hiker and you want to move from this area, this patch of trees here, up to a higher area, you don't want to drop down into a valley or go up over a mountain peak. Similarly, if you are trying to move upward in climate space to a slightly cooler area, you don't want to drop into a warmer area or go up over a snowy mountain peak to get there. You want, just like the hiker, to take the gentlest climatic gradient and avoid changes in temperature that are unnecessary, just like a hiker would avoid changes in elevation that are unnecessary. Again, this was published using with NPLCC funding. And this is an example of what the results look like. The tool will automatically identify the temperatures of different patches. It will use user-defined rule sets to decide which patches to connect. And that's this stick network here. And it will then map the least cost corridor connecting patches, both avoiding human heavy land use and following gentle temperature gradients. So you can look underneath these core areas and corridors and see that this follows a very gentle change in climate, a monotonic change in temperature, going from this warm area down in the Puget Trough up into the West Cascades. And before I turn this over to Mead, I want to mention that this has been applied now across the entire lower 48. This hasn't been published yet, but Jenny McGuire has looked at how to connect large core areas, large natural areas across the United States at different temperatures. So here we have warmer areas in red, going to cooler areas in yellow, green, and blue. And one of the upshots of this is that if you set a dispersal limit, say 100 kilometers, you will find that species in the Midwest will likely have a very hard time keeping up with climate change, both because of the heavy fragmentation here. There are not that many large habitat patches to move from or to, but also because of the high climate velocities in this area, because climate change will require movements over great distances. These networks are going to be of less utility than in more mountainous areas where species could move fairly short distances, a few kilometers, a few tens of kilometers, and stay within their current climate envelopes. And I can get back into that more in question and answers if people are interested. But the upshot here is that this is being applied to large geographies. It has not been applied in Alaska or BC yet, but these tools are meant to be readily applicable to new landscapes. They're freely available online. We have the tools and reports describing how they're applied at waconnected.org, and they are packaged as ArcGIS toolboxes. These are Linkage Mapper is being used all over the world now. Climate Linkage Mapper is beginning to be picked up. It's a more recent tool. But these tools are certainly not limited to Washington State. And just to recap, these are tools that can help to map wildlife corridors, climate corridors, the most central, most important core areas and core corridors in a network, barriers and potential restoration opportunities, and pinch points or vulnerable bottlenecks in corridors. And with that, I'll turn it over to me to give a more detailed example of how these are actually applied and some of the more nuanced issues of interpretation that go along with any kind of connectivity mapping project.
Thanks, Brad. Can you guys hear me okay?
Yep.
Okay. So as Brad said, I'm going to walk through an example of how to apply the tool to sort of a full landscape and how you might then interpret the results and actually use them to guide some decision-making on the ground. I'm going to apologize in advance that the example that I'm going to provide is not actually from the NPLCC region. So as Brad said, this was a leveraged project with the NPLCC supporting the tool development, but the GNLCC supported implementation of the tool. So the example is actually from the Columbia Plateau, but the tool and the analysis and the interpretation steps, all of that is really exportable to the NPLCC in really any region. And we are now, in fact, looking at Western Washington, the Puget Lowlands, the coastal areas, for a future analysis. So that hopefully is going to be coming up sometime in the near future. Okay, so as I was saying, I'm going to walk through an example and talk a little bit about who's using the tool too and how you might use it. So we first released a report in 2013 where we analyzed climate gradient corridors using Climate Linkage Mapper in the Columbia Plateau. And this is actually after our statewide analysis, which I'm not really going to talk about much, but our Columbia Plateau climate gradient corridor analysis identified here, these are the core habitat areas, these colored polygons, and they're shaded to reflect the mean annual temperature of these polygons. So here's a warm patch in the center here, moving into cooler colors and cooler temperature patches as you move up out of the plateau. The Climate Linkage Mapper connects any patch that differs in temperature by at least 1 degree Celsius, although I think you can actually modify that as you wish, but right now it's at 1 degree Celsius. And it connects them using these climate gradient corridors that avoid developed areas, areas of high human modification, and follow a relatively gentle climate gradient. So together this is the network, the cores and the corridors that connect them. So we're getting ready right now in the next month or two to release an addendum to that report, which identifies pinch points and barrier and restoration opportunities in the climate gradient corridor network for the Columbia Plateau. And the report also provides quite a bit of guidance around how to interpret the results. So as will become clear, the maps by themselves, the output of the analysis, it doesn't tell you by itself what decision you should make at all. You really have to take time to drill in and look closely at the linkages with other pieces of information, other sources of data to try to figure out what the results mean and what it actually should say about your decision making. So for example, here's the pinch point analysis for the climate gradient corridors. And what we're looking at here in green, these are the core areas. Again, they're not color-coded anymore by temperature because it's just too confusing with too many colors. But in green, we have our core patches, and you can assume that we're only connecting warm and cool patches. And then anything that's not beige, essentially, so anything from black to blue to yellow to red, is part of the climate gradient corridor network. So these are all the corridors that attach these patches. And in black areas and blue areas, movement is relatively unrestricted along that patch. But in the yellow areas and the red areas, we're looking at pinch points. So these are areas where movement is being funneled through a relatively narrow area. And that can make these corridors vulnerable to further habitat loss because loss of a relatively small area could sever the linkage entirely. So that's why these are priority areas for connectivity conservation. But again, if you just look at this map, it's not necessarily clear what to do with this information. What do we do about these pinch points or these other areas? And so, again, you want to take a look at some other sources of information and really kind of zoom in to figure out what this means for your decision making. And so here's an example where if you look down in the southeast corner of the plateau, what you see is that most of the climate gradient corridors in the southeast plateau are pinch points. The entire corridor for these circled areas is essentially one long pinch point. And what that means is that there are relatively few options for moving between warmer and cooler areas in this area of the plateau. So movement is going to be constrained within these really narrow, long corridors. And if you take a look like at Google Earth or other maps, what you can see is that these corridors actually fall along riparian zones. So each of these ones, these are long riparian zones along streams that link warmer to cooler areas of core habitat. And that makes sense because riparian areas tend to be in relatively good condition in these areas relative to the surrounding landscapes, and they follow climatic gradients. It's not really that surprising, but that does tell you something about what to do next, which is linkages between warm and cooler areas in this part of the plateau really needs to focus on riparian maintenance and restoration. And if you zoom in even further, so here now we're looking at a single one of these pinch point linkages, you can further prioritize within the linkage. So here we have one of the very hottest patches in the plateau of juniper dunes, and it has a linkage up to cooler areas to the northwest. And what's going on here is that up to this point, there is a single linkage, a single pinch point linkage that takes you up to the northwest, which then splits here into 3. And so at this point and onward, you have some redundancy in the corridor. So if you lost any one of these corridors, that wouldn't be great, but it wouldn't be the end of the world. You still have 2 other opportunities to move into a cooler area. But if you lose anything below this arrow over here, you're in trouble because now you have no way really of getting out of that core and moving into a cooler area. So this would be really the priority area for maintaining some climate connectivity in that area. So that's one way that you can really zoom into these maps and figure out how to prioritize where to be directing your connectivity conservation effort to maintain some movement, some permeability under climate change. So now, the pinch point analysis actually doesn't tell you anything about the quality or of the habitat in those pinch points themselves. So it might be in good shape, it might be in bad shape. It's going to find the least cost path regardless, and so barrier analysis can tell you a little bit more about the condition of these corridors and where there are barriers in them that if you address them, you could really improve connectivity through this landscape. So here's our barrier map, and again, in green here, in dark green, you've got our core areas. And then anything in blue through green and red is our climate gradient corridor network. So any one of these is a corridor, but here we don't really have many barriers. So that same pinch point, that same corridor that was a pinch point I just showed you, the good news is there actually aren't that many high impact barriers along that, so it's in pretty good shape, so that's good news. But we have other areas where we have major barriers between our core areas along our corridors, and we want to look closer to see what we can do. What are those barriers? What's forming them? And that can tell us something about how we can address those barriers and improve permeability between our core areas. So let's zoom in again here, and now we're looking at sort of the central western portion of the plateau. And if you look at just Google Earth or look at some other maps again, you can do this pretty quickly and you can figure out what these barriers are. And here what we've got going on is basically a whole bunch of roads that are bisecting our core areas, and they're forming the barriers. So here we've got I-90 severing an otherwise pretty intact area here. We've got I-82. We've got a bunch of state roads sprinkled around, and all of these are basically chopping up our core areas and forming barriers to permeability between warmer and cooler areas. So if you wanted to address these barriers, you'd really want to talk to someone like DOT about mitigating the impacts of these roads by installing culverts or other wildlife crossings. You'd want to bring in some other sources of information to narrow in on where would be the best place to do something like that. So bringing in information like roadkill data or other sources of information to figure out where things are already crossing the road. The other thing to keep in mind is that if you look closely, it's not just the roads, but things that come with them. So people live close to these roads. There's more agriculture, so there's actually other sources of resistance and barriers that are closely correlated with the presence of roads. And so that would also tell you something about what decisions to make. If you look closely and you see that in one area along the road you've got a town, whereas down the road you've got some farmland, that is going to be an easier barrier to restore than the town. So not all barriers can be restored. If you're looking at a focal species, for example, you can't necessarily restore a cliff that something can't cross, and you can't necessarily restore a city. But you can work with private landowners, for example, then to address, to mitigate the permeability or improve the permeability of private lands. And another thing to note that for the climate gradient corridors, of course, we can't address climate barriers. So a cold peak that falls along a relatively gentle gradient or a hot valley, you can't restore that. So we're really talking, even for the climate gradient corridors, about restoring areas that are impacted by human land use only. And then finally, to make a decision, you really want to bring in other sources of information. So I wouldn't recommend using the climate gradient analysis, for example, by itself to make any decisions about where to put my effort. I would want to bring in other conservation values. For example, here we've overlaid our results from the climate gradient analysis with the results from the focal species analysis. So now we've got 11 focal species looking at their pinch points on the left here and overlaid them with our climate gradient linkage pinch points. And so the circled areas here, the areas that are yellow or red, those are areas where there is agreement between focal species and climate gradient pinch points. And on the right, we've circled areas that are also barriers for both focal species and climate gradient linkages. And often they're sort of complementary, where you have a pinch point connecting a warmer to a cooler area and then a barrier running through it here. So this is, a lot of times it's a pinch point being bisected by a road, for example. And so these areas of agreement that are important priority areas for maintaining connectivity for focal species as well as for climate connectivity, those are probably some pretty good bang for your buck because you're going to improve current or maintain current connectivity and thinking about future connectivity as well. So there's any number of other conservation values that you all have that you would want to bring in that would be relevant for your objectives or mandates. And so this is just one other thing to keep in mind is that really these layers are probably best used integrated with many other conservation values to finally make a decision on where to put your effort. So just some take-home points is that the Linkage Mapper tools and Climate Linkage Mapper can help to identify priority areas for connectivity conservation. The maps by themselves, just that first product that you get out really isn't going to tell you what to do. You really have to do some thoughtful interpretation, bringing in other sources of information, other conservation values to make that final decision. And again, integrate it with those other conservation values. And then also remembering these are models, so of course, they're going to be wrong. You want to go ahead and do some serious ground truthing, check at least, starting with Google Earth, take some field trips, make sure that what's on the ground actually seems to agree with what the model was telling you. And then ultimately, these can really be used to inform some pretty diverse management decisions and users. So just some quick examples. The EPA used our statewide results as an additional layer for identifying green infrastructure, so areas that need to be avoided as part of the Transportation 2040 prioritization tool. U.S. Fish and Wildlife, BLM, and the Nature Conservancy used our Columbia Plateau results as part of, or the focal species Columbia Plateau results as part of their Arid Lands Initiative analysis, which identified collaborative conservation priority areas in the Columbia Plateau. And then Washington Fish and Wildlife incorporated some of our statewide results into their statewide chat, which is their crucial habitat assessment tool, so a mapping tool to identify priority areas or important habitat areas for wildlife in Washington State. So there's a really diverse ways that you can bring this information into your work. And you can find, for some guidance on how to complete these analyses, how to interpret that. We actually have a lot of guidance on how to interpret the results from these kinds of analyses, and also to find out how to access the tools. You can go to waconnected.org. That's the website of the Washington Connected Landscapes Project, and all of our analyses and reports and layers can be found at that website. And finally, Brad and I just wanted to thank the entire Washington Wildlife Habitat Connectivity Working Group. A ton of people put their time and effort into developing these tools and analyses with generous funding from the North Pacific, Great Northern LCCs, the Bureau of Land Management, and Wilberforce Foundation. And any questions, you can please get in contact with Brad at mcgray@circuitscape.org, or you can contact me at mcrosby@uw.com. Thank you.
Boy, thank you, Mead, and thank you, Brad. Great presentation. I think you really hit the mark of showing not only the science behind this, but also the tools that are available to help managers apply this stuff to their regions and districts. And just so everybody knows, we had a large number of participants in this call all over the U.S. and from Canada as well. So it's great participation. We'd like to unmute your phones now and allow you to ask questions. If there becomes too many trying to speak at once, we'll mute people and moderate them one at a time. But for now, let's just go ahead and unmute it. And if you have questions, just feel free to toss it out there for either Brad or me. Question that's already been submitted over the chat, I'll just voice it to you now. And the question was, which species or organisms did you focus on to create this model? Which ones are they related to? And if the answer is individual species, we want to hear that, and then if the answer is this applies to a suite of species, please describe that as well. So either Brad or Mead, feel free to take that question.
So I'll take a first crack. The answer really is both. That we focused on focal species. So these were species that were chosen to represent a large suite of other species. So in our first statewide analysis, we stratified the state by vegetation type and chose representatives of those vegetation types. We also chose species that were good dispersers, that had long dispersal distance abilities, and species like the western toad that had very limited dispersal ability. So we tried to catch a range of habitat affinities, and dispersal capabilities. What I didn't mention in my first part was that we also mapped connectivity for landscape integrity, basically in choosing large patches of natural habitat and connecting those patches via corridors that also followed natural vegetation types. So that was also meant to catch or to model connectivity for a suite of species and not only a single species. And we have some composite products that actually combine barriers, pinch points, corridors across focal species in order to see where you have areas that are important for connectivity for many species, not just single ones.
Great, thank you. Any questions from the audience right now? We have a couple more on the chat line. Let me toss one out there. One question was, has this, either Brad or Mead, has this connectivity analysis been applied to waterfowl and wetlands?
It has not in our area. I'm not aware of applications of all of of most of these tools to waterfowl or wetlands. There have been some limited applications to riparian areas and riparian-associated species like salamanders, but those are fairly few and far between just yet.
Great. We have another question here about the land use changes, and if you are able to model how humans will shift their land use in response to climate change, either through agricultural areas shifting because of droughts and drying to other regions. So obviously you modeled how animal species are likely to shift. Can you take into account how land use is likely to shift in response to climate change as well?
Yeah, this is something we've talked about quite a bit. It's certainly something we've thought about. We have not addressed it yet. I don't know if we necessarily will. It's certainly something that's worth looking at. I think my personal bias would not be to include it in the initial model, but as sort of a follow-up model, something to look at to compare with the initial results, because then it could tell you something about how your model might change given patterns of future human land use, how you might sort of pick your battles given where people might be moving in the future, rather than sort of incorporating it in the beginning and then having a little less clarity about what's driving the model and what's under the hood. I like seeing the components of the model broken out separately so it can better inform your decision making and be more transparent. So yeah, that's a great question. We just haven't done it yet.
Are there any plans to do this for the whole geographic region of the Great Northern LCC? And maybe I'll expand that question and ask, are there plans to expand this further to the north or south or through other regions that you're aware of?
We wouldn't be doing it. The Washington Connected Landscapes Project, the entire GNLCC is just out of our geographic range and that of our partners. And Brad, you can certainly speak to this as well as I could, but the majority of our member organizations are really focused in Washington and with questions in Washington and surrounding areas, and so I don't know that it would be the place of the working group to do that. Certainly Jenny McGuire's work and others' work is sort of building off some parts of our analysis to look at the entire 48, but I don't know of any application of our suite of methods to the GNLCC. I don't know, Brad, do you know of anything?
Not at the moment. There's certainly a lot of work going into some transboundary connectivity issues. But one of the limitations is data availability. There are fewer data sources for high-quality land use data available in Canada just yet. I do know some folks that are working on improving that, coming up with some land use data sets for North America, and that could really facilitate an application like what Jenny McGuire is doing across the lower 48, but extending up into Canada and Alaska once that comes online.
Right. Well, it seems like this methodology is transportable to other regions, other countries, and at a larger scale, it helps really provide some strong guidance for landscape scale conservation. So I think it's, if the desire is there and the funding is there, it sounds like you can use these tools to crunch through those data if the data are available as well. Another question is, did you model for shrub, steppe, obligate avian species?
We did model sharp-tailed grouse and greater sage grouse, and we have corridors, pinch points, barriers, and centrality maps for those in our Columbia Plateau report on wallconnected.org.
Great. Any questions from the audience? I have one or two left on the chat, but I want to allow those of you who want to ask questions or have a dialogue with the two PIs to go ahead and feel free to do so.
Yeah, I tried to type one in, but I'm just wondering how the core areas were determined.
Yeah, and that are you referring to focal species or the climate analysis?
They were different core areas?
Yeah. Yeah.
Well, then both.
Sure. These, for focal species, we actually termed these habitat concentration areas. We used a set of GIS tools that have now been released as part of the gnarly landscape utilities that I mentioned, along with mostly expert-driven models of habitat suitability. So in most cases, this included vegetation, land use, roads, power lines, other features that experts in the Washington Connectivity Working Group identified as important for each species. And those models were then used to model core habitat areas. For the landscape integrity analyses, and that's a portion of the project that John Pierce led, and also for the climate change analyses, we used similar models, but those focused on intensity of land use. So areas that were intact and had few roads, few human land uses, were clustered into, and we had a size threshold of 10,000 acres for the smallest qualifying core area. And then those were connected. So two different approaches, parallel approaches essentially between the focal species and the landscape integrity / climate analyses.
Great. Any other questions from the audience? The next question we have on the screen really is related to who do people contact for more information on this, if they're interested in applying this to their landscapes or just following the progress of this work in general. And as you see on your screen, the email addresses for both Brad and Mead. I'd also suggest you look at some point at our YouTube channel if you want to review this webinar. We've recorded it. It'll be available on our NPLCC YouTube channel. And also track this project and other projects through the NPLCC resources page. We post a lot of information about the projects and progress reports and final reports and various tools on our resources page. And that's a great way to keep track of this as it evolves and grows across the region. Before we sign off, I'll open it one more time for any questions and see what else, if anybody has anything else they'd like to ask.
I'll add one more thing, which is that there is a listserv for the Washington Connected Landscapes project. So if you go to Walk Connected, just look at how to sign up for our listserv, and we have, I'm not sure quite how often, but there's newsletters, and anytime we release new products, there'll be an email sent out, and there's also occasional webinars.
Yeah, great point. That's a really innovative group, and it's amazing the amount of work that they've done, how they've been able to leverage that work and grow both in scale and geographic region. Another question here just popped up, and that is, how do broad-scale, is it possible to do broad-scale connectivity planning with these tools for migratory birds?
It's certainly possible. Migratory birds are a little bit different in the fact that they're going to be able to cross barriers in ways that many species can't. But the Linkage Mapper toolkit could allow you, for example, if you had a set of stopover wetlands or stopover habitats for different species, you can quite easily define rules saying what is the longest dispersal hop that a species could make from one stopover area to another. And then you could create a network of stopover sites, and it could show where you have lots of redundant areas of connectivity and areas where you might only have where one stopover site could disconnect the entire network if it is lost. So there's certainly ways to adapt these tools to different dispersal behaviors and capabilities.
I just have a comment and a question. I think the creativity, the science, the innovation that Washington Connected Areas has shown us is an inspiration to a lot of us working in this quadrant of the continent. The question that I raised earlier with regard to the scaling of these things, I think there's intense interest in that at the present moment of time. John Pierce is leading a landscape initiative on the GNLCC, which is looking at connectivity at the meso-regional scale, and we're looking at human modification indices across the GNLCC, and the climate change stuff is a no-brainer to do the same thing with. So I think the scaling applications are almost unlimited. A lot of the data issues are often to deal with the accessibility of information on the Canadian side rather than its availability. I think that's particularly true in Alberta. Finally, I just wanted to end up with a question. How soon will this one be posted to the LCC website? This would be a really good presentation that I'd like to show a bunch of other folks.
Thank you. We're going to try to get this posted by the end of today. If not today, it should hopefully be up tomorrow, but I'll make sure to send out a link to everyone that participated today as soon as it's posted.
Thank you.
Yeah, I don't think so. Why, you're not here? I'm not here.
Any last questions or conversations we want to have before we thank everybody and sign off? I'd like to thank... go ahead.
I'd be curious as to what sort of internal coordination is happening within TNC and as regards, methodologies for doing these types of analyses. I'm in the Northeast, and they're doing some similar things here, but I'm wondering, is there coordination, or is it more project specific in terms of how these things are developed?
Yeah, unfortunately, it's somewhat project-specific right now. I'm supporting various efforts on connectivity, applying some of these tools actually to, for example, for modeling fire movement and fire risk, sage-grouse connectivity in southern Oregon. We're working on connectivity, a Duke-funded project that you're probably aware of that incorporates wall-to-wall connectivity with Mark Anderson that's been applied in the Northeast, and with another team that's been applied in the Northwest. But it would be nice to get a bit more internal communication going on these methods, and a little more coordination on how they're applied. Please feel free to shoot me an email on that.
Yeah. I was wondering about the large landscape conference and whether you guys would be attending, and whether that would be a place to, get a discussion going around this.
We were not planning to attend. I'm aware of that conference, but that's it certainly could be up for negotiation.
Okay, I'll send you an email.
Sounds good.
Thank you.
This is one of the reasons we like to advertise these sorts of webinars far and wide, because it often is the case that people in other regions, other parts of the U.S., or even in other parts of America are struggling with similar approaches. And if we've invented a great technique or we've helped fund a great technique, we want to share it broadly so we can create some efficiency in the system and advance conservation without having to reinvent some of these tools. So I'm really thrilled to hear some folks from outside of the traditional NPLCC, even the Great Northern region, are participating on this call, and I think it's helped speak to that need as well. Well, let me just wrap up and thank both Mead and Brad for joining this call, for doing this work. I think this sparked a lot of conversations, and there'll be a lot of follow-up information. We had several additional questions and complimentary messages over the chat line that I'll be happy to share with the presenters. But overall, I think it was a great webinar, and I really look forward to continuing the dialogue with conservation partners across the world and how we can share this tool with others. So thanks again, you all. Please feel free to visit our website, contact the presenters directly, or look at this presentation again on the YouTube channel. Thanks again.